Okay, thank you. So I'm from Laboratoire Kastler-Brossel in Paris, and my talk will be about the simulation of quantum Hall physics using dysprosium gases, and as you will see, using many spin states of this highly magnetic atom. Let me check. Yes, it works. And so, yes, indeed, you don't see the pointer, but anyway. So I will start by reminding you maybe the different techniques that have been set up to simulate magnetic fields for ultra-cold neutral atoms. Then I will tell you how we implemented that using the concept of synthetic dimensions using an atom, dysprosium, which has a very large number of internal states. And then I will present to you a more recent project about the study of topological phase transition. Maybe briefly, I remind the big successes of quantum simulation with ultra-cold atoms. I will be extremely brief. So quantum simulation has been very successful, for instance, to study the BEC-BCS crossover with strongly interacting fermions. Using optical lattices, we could study many interesting phases of matter, such as Mott insulators, for instance. But here we are interested in the simulation of another class of phenomena associated with the quantum Hall effect. And the big challenge is that when using atomic gases, the atoms are neutral. And so we have to simulate the action of a magnetic field acting on a charged particle in an artificial manner. And so this is what I will explain in the first section. What are the different techniques to achieve that? So historically, if I start by the first one that was implemented, it was by considering rotating gases, so subjecting the gases to a rotating perturbation and looking at the gas in the rotating frame. And then we know that the atomic motion is perturbed, or has to include the Coriolis force. You see here the expression, and you will recognize that it is formally equivalent to the Lorentz force that acts on a charged particle when you put a magnetic field. Then this leads to essentially the same physics. And in particular, in Bose-Einstein condensates, it leads to the appearance of quantized vortices, a little bit like the action of a magnetic field on a superconducting system. So this was done in the early days of Bose-Einstein condensation. And more recently, there were very nice experiments, in particular in the group of Martin Verleij, where he could show really dynamics of atoms in the equivalent of Landau levels, which are the bounds that a charged particle has inside a magnetic field. And that gives rise also to chiral edge modes, as you can see on this picture. So the gas initially in the center spreads, and when it hits the walls, circulates around with a given chirality. Okay. Another class of technique is to use atoms in optical lattices. So the atoms are held in a discrete set of lattice wells and can hop via tunneling from one well to another. And to simulate a magnetic field, the idea is to stimulate the hopping process by the absorption of light, such that the matrix element that connects, that describes the hopping between two positions, involves the electric field absorbed, the electric field of the absorbed photon, and this electric field has a complex amplitude that depends on position. So in that way, the matrix hopping element becomes complex, and this is very similar to the action of a magnetic field on a charged particle that gives rise to the so-called Aharonov-Bohm phases, which are called in lattice systems higher phases. So I'm fast because it's not exactly what I will explain later, but it's somehow very much related. Okay, so in lattices, this leads to the simulation of topological bounds. And I flashed here maybe an important result where it was shown that when we prepare atoms in the lowest energy bound, it exhibits a quantized Hall effect, meaning that if you apply a force along a given direction, the cloud drifts in a perpendicular direction. And you see here the drift as a function of time, which agrees well with this straight line that represents the expected quantized Hall drift when you have a field, uniformly filled topological band. Okay, and last, there was another family of technique developed to simulate magnetic fields, which is the use of so-called synthetic dimensions, which means that in those systems, one replaces one spatial coordinate, let's say y, by an internal degree of freedom. So this is a picture taken from one of the first experiments, where you see here on the y-axis 3 spin states that acted as 3 effective sites of a synthetic dimension. And this was sufficient to observe chirality, if you wish. And so, naturally, this motivated extending this technique to atoms that have a very large spin, such that we can use a very large number of internal states. So this is what we did, choosing dysprosium. So dysprosium is an lanthanide atom, where in the electronic ground state, you have in the submerged F shell with 4 electron vacancies, which combine give rise to an angular momentum J equals 8, which means 17 magnetic sublevels with a quantum number n ranging from -8 to +8. So these are the degrees of freedom I'm going to consider. So as I said, there are 17 states in the internal structure of the atom. And then we will consider another dimension, which is a spatial dimension, the position of the atom along a given direction, which is the direction along which we send a pair of counter-propagating lasers. And we will disregard completely the other 2 spatial directions because they are decoupled. So we will consider an effectively 2D system. And the occurrence of a magnetic field, as we will see, comes from the fact that we induce a dynamics between the successive magnetic sublevels via 2 photon Raman transitions. So more specifically, we increase the magnetic projection by absorbing 1 photon from the laser going along -x and emitting a photon in the mode of the second laser. And when doing so, we exchange momentum between the atom and light, and the atom receives overall a momentum kick -2 h bar times the light momentum along x. And this gives rise to a magnetic field, an effective magnetic field, and I want to give you 2 visions of that. That are relatively simple, I think. One is to see that there is a conservation law. As I said, when the magnetic projection increases by 1, the velocity decreases by this amount, this quantized amount, which means that if we write a dynamical equation, the time variation of the velocity is minus h bar k over the mass times the time variation of the magnetic projection. And I write below the equation of motion of a charged particle due to the Lorentz force. And you see that the 2 equations are essentially the same as soon as you say that n plays the role of light. So we have a Lorentz force. Another way, which is a bit the same thing in a sense, is to say that when we hop from n to n plus 1, Then this occurs via the absorption of photon in laser 1 and the emission of a photon in laser 2. And so the hopping amplitude is proportional to E1 times E2 star. And then this gives rise to a complex phase, E minus I kx, where k is twice the light momentum. And this is equivalent to having a vector potential that would be along the n direction and with an amplitude that depends on x. So again, this is what we need to have a magnetic field. Okay. So now, what does it give in practice? So I plot here the dispersion relation of the system that we consider in the experiment as a function of the momentum, which is the kinetic momentum plus h bar k times the spin projection. This is conserved by the Raman transitions. And well, what you see is that you can see that in the middle you have a series of quasi-flat bands that are the equivalent of Landau levels. And on the side of this dispersion relation, you recover half parabolas that correspond to chiral edge modes. Okay. So now let's switch to the experiment. So we use atomic gases right above the critical temperature, so in a subrecoil temperature regime. And we start with the atoms polarized in n equals minus j, so the lowest Zeeman sublevel. Then we shine the Raman lasers. And we play with the detuning between the Raman lasers to basically induce a force along x on the atoms. It's an inertial force when we place ourselves in the frame of reference moving with the Raman detuning, if you want. Okay. Once we have prepared the momentum state we want, we probe the system. So we take an image. And so this is a typical image. And well, we take it after time of flight, so the position reflects the velocity of the atoms. And during the time of flight, we apply magnetic field gradient, so the spin states separate. So in a single picture, you have both the velocity distribution along x and the spin composition, as you see here. And so I will show you this spin-resolved velocity distribution when we go across the ground bound of the system. So if I go back to the dispersion relation, we start here. So the system is polarized in the spin minus 8, equals minus 8, with a negative velocity. And then we apply a force to adiabatically follow the ground. So on this graph, the x-axis is the velocity, the y-axis is the magnetic correction. So we start, as I said, in minus 8 negative velocity. We apply a force. So the velocity approaches 0. That's pretty normal. And there are no Raman transitions because they are off resonant because of the Doppler effect. But they become resonant when the velocity approaches 0. And you see that we start populating 7, minus 7, minus 6. And then, okay, we start doing a series of Raman transitions. So this can be seen as the bulk of the synthetic dimension. And you can remark that despite the fact that we apply the force on x, in this regime, the velocity remains more or less 0 on average, but you have a transverse drift along the vertical. So this is a whole drift, and eventually we reach the top. And then we are on the top edge, and we recover a ballistic motion with positive velocity. So I think you have here in this picture all the quantum Hall physics, the transverse response in the bulk, and the ballistic chiral bond here and here. Okay. So this was basically a project that we did quite a long time ago now. And I want to present now a more recent project that we put on archive in March of this year, which is an extension, if you wish, of this setup, where physically we have not made things much more complicated. We have simply added on top of the Raman lasers an optical lattice along the same direction. And so you have the competition between the Raman couplings. So they are described by J plus, J minus spin operators with these higher spins. This is what I already used in the previous part. And so we add now an optical lattice that has, it uses the same color, so the same light momentum. And so we are going to study what happens as a function of the ratio between these two quantities, the Raman and Bragg processes. And I parameterize the ratio by a parameter lambda. So lambda equals -1, only Raman lasers. Lambda equals +1, only lattice. And well, the quantum Hall properties, they are described by an integer, the so-called chair number that tells you what is the Hall conductance in unit of the quantum of conductance. So we know that on the left, when we have only Raman bits, the chair number is equal to 1. On the right, if you have only a lattice, there is anyway no spin dynamics at all, so there will be no transverse drift, so there must be a chair number of 0. So it's clear that at some point there will be a topological phase transition. This is what we want to study. Okay, we can actually visualize that by treating the spin degree of freedom semi-classically. So it's not an exact treatment, but it will help us understand this phase transition. And also, so we have the 3 spin operators, and I will assume that we are on the equator, so we are in the middle of the bulk, if you want, so the magnetic projection is close to 0. And so I'm interested in the evolution of the azimuthal angle of the spin. So the Jx, Jy are J cosine phi and sin phi. And then if I go back, J plus will be given then by J E I phi, J minus by J minus E minus I phi. And so the Raman coupling becomes cosine Kx minus phi that competes with cosine Kx. And, okay, so this is what is plotted here, this potential, where on the x-axis I have this azimuthal angle phi, and on the y-axis I have x. Actually, the idea of doing that is that when we want to study the Hall response, we are going to apply a perturbation, and we are going to look at the transverse response. So the perturbation can be a force along the spin dimension, which is a perturbation proportional to the spin coordinate, h bar omega z j z, which drives a Larmor precession, which means that phi will increase linearly in time as omega z t. And so when we plot this potential, we will assume that the particle will be driven by, on the x-axis, by a weak force along the synthetic dimension, and the whole response will correspond to the motion of the particle along the bottom of this potential. So let's start by this potential purely. There is no lattice, only the Raman coupling. So cosine Kx minus phi. So this is the potential landscape. And the minimum is plotted in the red line, so it's obviously increasing linearly. So it means that each time we make one Larmor rotation, the particle has shifted along x by lambda over 2. So this is the quantized Hall effect visualized in these terms. So now let's make these two contributions compete. So I increase a little bit the lattice. And I plot always the potential as a function of the time. And you see that it deforms, but the particle always drifts by lambda over 2. Until there is a discontinuity at lambda equals 0. And then, after we pass the discontinuity, the minimum of the potential does this kind of trajectory, and there is no more Hall drift. If you have a question.
Sorry, just because in the previous part you said that the quantized Hall drift was along the vertical direction, like the synthetic dimension, and now you kind of the other.
Yeah, I'm allowed to change. It's actually a bit simpler to explain if I flip.
Okay, but it's the same.
It's the same, yes. Yes.
Because you change the direction of your effective force, right?
Yes, here it's a bit simpler if I say that the force is along the spin direction.
Okay.
But you will see when I will speak about the experiments that we do the opposite. But, okay. Sorry for that. Sorry, I'm not speaking. Yeah, okay. Yeah, so I continue increasing lambda, and obviously when I have a pure lattice, then there is no more spin, no more coupling between spin and exposition, so there is no Hall drift. And so we see there the transition between quantized non-trivial Hall drift and the trivial insulator. Okay, so now I move to the experiment, and indeed, for the experiment, we do the opposite experiment. Let me explain what we do. So it's a little bit different compared to the case I explained in the second part of the talk. So here we prepare actually a statistical mixture of all spin states to begin with. So we kind of populate the ground bound in an almost uniform manner. And basically the starting point is this distribution. So this is the probability to be in a given M state. At the beginning, once we have loaded the atoms in the Raman and lattice potentials. And then we apply a force along X, which corresponds to one block oscillation. And we look at the new spin distribution. And what you see is that when we push the system to the right, the particles shift upwards. And in the end, atoms have left the bottom edge and have increased in the top edge, and vice versa in the other direction. So basically, if we look at the accumulation or the change of probability in a given sector here, this corresponds to what has crossed this line, and this corresponds to the local Hall current. And this can be represented as a local Hall response, or more technically, a local Chern marker as a function of the position of a link at which we look at the Hall response. And you see that in the topological phase, we have a Hall response which is quantized in the bulk, and it decays a little bit on the edges. So we can compute this Chern marker as a function of the parameter that describes the competition between Raman and lattice potentials. And so in dark blue, you have a Chern number of 1 here, and in light blue, a Chern marker of 0. And so this gives us basically the topological phase diagram. So more specifically, if we look at the middle of the synthetic dimension, we have a transition between two plateaus with a Chern number of 1 towards a Chern number consistent with 0. With a certain slope in between, we have a crossover, which is due to both the finite size of the synthetic dimension and also the fact that we perform the experiment with a finite force. So there is a well, this explains the smooth crossover. Okay. Maybe to show that this change occurs precisely at the phase transition, topological phase transition. We also identified when the gap closes in the band structure. And for this, when we perform the block oscillation, we can measure at the end the probability to end up in an excited band using a standard band mapping technique. And so this is what we measure as a function of the parameter lambda. And you see a maximum at lambda equals 0, which indicates that this is where the gap between the ground band and the first excited band must vanish. More precisely, also, we studied the probability to end up in an excited band as a function of the duration of the block oscillation. And we started in the trivial insulating phase, where we have a ground band that is well separated from higher bands. So this is the expected band structure. And then the probability to be excited after one block oscillation has a characteristic Landau-Zener behavior. So this is quite expected. I will conclude quickly. If we do the same in the topological phase, we have a very similar behavior. But if you look more closely at the band structure, basically the dispersion relation has a band that is kind of gapped with respect to the first excited band, except that there are two branches due to the chiral edge modes. So it means that when you look at the excitation to higher bands, there is a Landau-Zener formula, a decay, but towards a non-zero value, which is due to the fact that when we make a block oscillation, we have to be diabatic along these edge modes. And finally, when we are at the critical point, this is the dispersion relation that we expect. You see that there is almost no gap closing, only one due to the finite size of the synthetic dimension. And the signature of that is that the decay of the excitation become algebraic, which is typical of a gapless structure. Actually, it seems that I'm out of time, so I will have to skip the following. But the decay that we measure is characteristic of the way the gap closes, which occurs via a Dirac point, which we don't see here very well, but in a sense, it's a discretized version of a Dirac point in a system with a finite synthetic dimension. And we could basically show that the band structure at criticality has a single gap closing point, which is a Dirac point, by looking momentum resolved at where the gap closes. So I skip the detail. And maybe the message I want to say to conclude is that when we are at the critical point, as soon as the gap is closed with a Dirac point, then we measure, when we make a whole measurement, we don't measure 0 or 1, we measure 0.5. And this 0.5 is actually not an accident, it's a protected result due to the fact that the gap is closed with a Dirac point, and it is the so-called Parity anomaly associated with a Dirac point as soon as it is placed in a lattice structure. Okay, so you see that when we change some parameters, like the duration of the block oscillation or the total power of the Raman and lattice beams, this 0.5 exhibits a plateau, which is characteristic of the robustness of this half quantization. Okay, I just want to thank the team. So this was the team in 2020, and this is the team that did the recent project on the Dirac point. Thank you.
So thank you very much. So just one quick question, because we're a bit out of time, if Yeah. Yes, please.
You don't see any effect created by the dipolar interaction, right?
No, because the experiments are very fast, because for the moment, in our current configuration, we have a lot of dipolar inelastic interactions due to dipolar relaxation. The reason, well, is that, well, we have a huge Zeeman splitting between different magnetic states. So as soon as your system is not in -8, it decays. And the lifetime of a BEC is about 1 millisecond. So, yes. So that's why we don't have a BEC, but we use a dilute thermal gas.
So thank you. Let us thank the speaker again.